Good morning viewers. In this video, I plan to discuss a few previous UGC net questions from group theory from that part involving matrix representation and character table. June 2011, given C3V character table and a reducible representation gamma as 630. What are its irreducible components? Its answer is a direct substitution in the reduction formula. Number of times ith irrep belongs to a reducible representation is 1 by order of the group sigma chi I r gamma r n r, where chi I are the characters of ith irreducible representation, gamma the characters of reducible representation, n are number of operations belonging to the class R. You are adding up over all the classes. Let us see how many times A1 type irrep belongs to this given reducible representation. It will be, you write the characters of A1 which are 1, 1, 1, then gamma is given as 630, number of operations in each class 1, 2 and 3. You multiply and add them up and put 1 by 6, 1 into 6 into 1, plus 1 into 3 into 2, plus 1 into 0 into 3. If one of the multipliers is 0, the whole thing becomes 0. So this will be 1 by 6 into 6 plus 6, or it is 2. So there are two A1 irreps in the given reducible representation. Similarly, look for number of A2 type. Character is 1, 1, minus 1. Reducible is 630. And number of operations are 1, 2 and 3. Multiply and add, divide with h, that is 6 here. 1 into 6 into 1. Plus 1 into 3 into 2. Here is a 0, so I will put 0 here. This becomes 1 by 6. 6 plus 6 plus 0. Again you get 2. There are two A2 type irreps also. Then how many E type is there? Number of E type irreps is character of E is 2 minus 1 0, reducible representation 630, number of operations 1 2 3, so 1 by 6 into multiply 2 into 6 into 1 plus minus 1 into 3 into 2 plus there is 0 here, so I will put 0. It is 1 by 6, 6 into 2, 12, 12 minus 6. So 12 minus 6 is 6, 6 by 6 is 1. So your answer is, there is an E type, there are two A2 and two A1. Among the options, the correct option is this one, E2A1 plus 2A2. Another question. December 2011. December 2011. Given the C2V character table and two functions phi1 p1 plus 2p2 plus 2p3 plus p4, and phi2 2p1 minus p2 minus p3 plus 2p4, where pk is the p orbital on the kth carbon atom of cis butadiene. Cis butadiene belongs to C2b group, and the sigma v is the molecular plane, and it is with respect to the sigma v, the subscripts 1 and 2 are given in the character table. Character table is identity C2 sigma v dash 1 1 1 1 1 1 minus 1 minus 1 1 minus 1 1 minus 1 1 minus 1 minus 1 1. This is A1 A2 B1 B2, and sigma v decides if it is symmetric with respect to sigma v. Subscript 1 is here. When it is antisymmetric minus 1, we have subscript 2. So this is the molecular plane sigma v xz. We shall draw the molecular plane as z and x, and the butadiene molecule may be shown in the plane in such a manner what will be the picture of phi1 in terms of the component p orbitals. These are the carbon-carbon bonds of butadiene. This is the molecular plane. This is the z and this is the x axis. This is P1. This is 2P2. This is 2P3. This is P4. When it is 2P2 and 2P3, I have drawn the dumbbell in a bigger style. Every p orbital has one lobe positive, another minus, plus minus, plus minus. This is the normal way we draw the sign of the lobes of p orbital. The whole picture represents phi1, and when you do identity over phi1, this picture does not change. So it is as if phi1 is multiplied by 1, or the character is equal to 1. Then if it is C2Z, this is C2, the 180-degree rotation about this axis exchanges P1, and this is P1 and this is P4, this is 2P2 and this is 2P3. 2P2 and 2P3 get exchanged, P1 and P4 get exchanged, and during this rotation, the positive lobe of any orbital, when it comes to the other side, goes below the plane of the molecule, and the negative lobe comes above the plane. So as if the whole set of p orbitals are multiplied by minus 1. Or we can say that phi1 on doing C2Z changes as if it is multiplied by minus 1. So the character becomes, under C2, becomes minus 1. Then reflection in the xz plane, molecular plane. There also we can see that the lobes are above and below the plane. Reflection will bring the positive lobes below the plane and the negative lobes above the plane, and the whole phi1 changes as if multiplied again by minus 1. Or we can say character under sigma v is again minus 1. Character under sigma v is again minus 1. But if you reflect it about this plane, why is it plane? The orbitals get exchanged, but the whole picture of phi1 does not change even with the Sign of the lobes, there is no change. So as if it changes, multiplied by plus 1. So the set of characters are plus 1, minus 1, minus 1 and plus 1. Such a set belongs to B2 type symmetry. Then let us draw the diagram of orbital phi 2. This is the Z axis, this is the Y axis. 2p1, I will draw it in a bigger style. Minus p2, this is plus p2 is like this, but minus p2, the upper lobe becomes minus, lower lobe becomes plus. Minus p3 is also similarly, the signs are changed, but it is plus 2p4, it is bigger in size, upper lobe plus and lower lobe minus. The whole thing is called phi 2. And when you carry out identity operation over phi 2, the whole picture does not change. So it is just like 1 into phi 2, or character is just 1. But on doing the C2Z operation, C2Z operation, this type of rotation is there. This 2p4 comes to the position of 2p1, but the signs of the lobes are interchanged. Signs of the lobes are interchanged. So also between p2 and p3, minus p2 and minus p3 get interchanged, with the sign also changed. So the whole thing changes as if multiplied by minus 1. Sigma v xz. Xz is the molecular plane, and the lobes above the plane come to below the plane, and the lobes below the plane go to the upper part, as if the whole set of p orbital arrangement here is multiplied by minus 1. The locations of the p orbitals do not change, but as if they are multiplied by minus 1, such a change occurs. So it is minus 1 into phi 2. And when phi 4 is done, what's phi 4? When the sigma v dash is done, sigma v dash, the whole picture of phi 2 remains exactly like that, as if multiplied by plus 1. So again the set of characters representing the transformation of phi 2 under the operations identity C2, sigma v and sigma v dash are 1, minus 1, minus 1 and 1, typical of B2. So our conclusion is the two p orbital functions written phi 1 and phi 2 belong to B2 type symmetry. B2 type symmetry. I think I forgot to mention the options. Options are like this. A, phi 1 and phi 2 are A1 and A2 respectively. B, both B2. C, both A2. D, B1 and B2 respectively. We proved that both belong to B2. One more question we shall discuss. December 2011, again. If the displacement vector components centered about every atom of cis-butadiene act as basis functions, what will be the characters of the reducible representation under the operations identity C2, sigma v dash. Sigma v again is the molecular plane. There are 4 options given. A, 30, 10, 30, 0. B, 30, 0, 10, 0. C, 30, 20, 0, 0. And D, 30, 0, 20, 0. This can be easily worked out if you remember the rule of predicting the character of a reducible representation on the change occurring to the basis functions. The rule runs like this. If a basis function remains unshifted during an operation, its contribution to character is the number 1. If a basis function gets bodily shifted to another location during any of the operations, contribution to character to the particular irrep will be the particular reducible representation will be 0. Complete shifting will make 0 contribution. Complete unchanged quality gives a contribution of 1. It is also possible during an operation a basis function remains in its original place but changes as if multiplied by -1. A vector that is direct pointing upwards may change to the same vector with the same origin but pointing downwards. In such a change, the contribution is -1. Here we have the 10 atoms in C4H6, that is the molecular formula of butadiene. And centered about every atom, there are 3 displacement vector components. It can be picturized like this. These are the carbon atoms and these are the hydrogen atoms. H, H, C, C, H, C, H, C, H, H. Let the displacement vector components about every atom is denoted by 3 arrows in this manner. This is the X component, this is the Y component, and this is the Z component. So about every atom I will draw 3 such vector components. Making a total of 3 into 10 or 3 into 10 or 30 displacement vector components. The 3 displacement vector components may be generally written as xi, yi, zi, where I is the number of the atom. So x1 up to finally z10. Suppose this is the atom number 1, hydrogen. I will write this as x1, this as y1, and this as z1. And all these are written, and finally if this is atom number 10, this will be x10, y10 and z10. So from x1 up to z10, there are 30 components. The operation of identity over this. None of these components get shifted. So contribution to character by every component is 1. So we have got 1 plus 1 plus 30 numbers, making a total of 30. So among all the options, the first number is 30. So we are not able to make a decision now. Then secondly, we have this C2Z. When 180-degree rotation is done about this axis, it is very clear that all the atoms to the right side of this line, both carbon and hydrogens, will be shifted to the left side and vice versa. So the whole atoms are shifting from one position to another position. And the displacement vector components also undergo bodily shift. So contribution from every component becomes 0. So the next one will be 0. Then there is reflection in sigma v, which is the xz plane. So all the x and z components, xi, zi of all the 10 atoms remain unshifted because they are lying in the plane. A vector component in a plane, by reflection in that plane, will not get shifted at all. That means for every atom, character is 1 plus 1, 2, and from 20 atoms, so from 10 atoms, 10 into 2, there is a contribution of 20 from the x and z components of displacement vectors from all the 10 atoms of cis-butadiene. Then, when reflection in the xz plane is done, the y component will be reflected about that plane and change as if it is multiplied by -1. So from every component there is a shift -1. So we have got -1 into 10, making a total of 10 minus 10, 10. So there is 30, 0, 10. And reflection in this plane, sigma v dash. All the atoms are shifting from left side to right side and vice versa. So the components also get shifted. Contribution becomes 0. So the correct answer is 30, 0, 10, 0. Option B. With this, we are winding up today's class. Thank you.